Okay, ladies and gentlemen, welcome to today's conversation on three parameter Weibull analysis. Now, full disclosure at the start, it's going to be helpful for you to understand what Weibull analysis is, let alone before we talk about what three parameter Weibull analysis is. And if you're not as familiar with Weibull analysis as perhaps you might like, that's all right. We'll try and go through the steps or explain that as we go. But regarding three parameter Weibull analysis, it is an extension to Weibull analysis. But there's certain times when it's okay to use three parameter Weibull analysis, and there's certain times when it's not okay. And when it is okay, there are certain things that can be really, really useful when it comes to three parameter Weibull analysis. And we'll go through what makes it potentially useful and what some of the issues might be. So, three parameter Weibull analysis. I'm going to start today's conversation with, you guessed it. Oh, come on, there we go. The ball bearing. Yes, the thing I use a lot as sort of my exemplar little item. Now, the reason we're going to look at this ball bearing, those veterans of my webinars and courses, you know, the ball bearing features a lot. We're going to really look at how a ball bearing fails at the first part of this conversation, because understanding how it fails sort of sets the scene for one way that a three parameter Weibull distribution might be able to help. So here's a ball bearing, wonderfully simple little item. And the ball bearing gets its first part of its name from the fact it has a bunch of steel balls within its design. The steel balls, in this case, 6 of them, are held in place using a cage. The cage is nothing structural or anything else. It's just the cage just makes sure that the balls don't touch each other. Now, the balls touch the inner ring, which is the ring on the inside of the ball bearing, and that inner ring has a groove, and that groove is the groove that the balls roll along. That's called the inner race. The outer ring can rotate the other direction, and it too has a groove that the balls can roll along, and that's called the outer race. Now, why ball bearings are so really useful as a product or component or whatever you want to call it, is because it allows the inner race, which is usually connected to or touching or somehow in league with a rotating shaft, to be held in place while the balls and the races essentially minimize the friction associated with turning. So you want to have a ball bearing like this hold a rotating shaft, and think of all the things in the world that have rotating shafts: ships, cars, manufacturing machines, you name it. And the idea of the ball bearing is that it's there to support a rotating shaft while minimizing the friction associated with that support. And the way it minimizes friction is by using the rolling motion of the balls. So nothing ever slides over another part. It's all about rolling. So let's zoom into the bottom ball of our ball bearing. So right down the bottom, you can see there's 6 balls. Let's go look at the ball right at the bottom and zoom in and see what we can see when we do. Now, when we zoom in and take a cross section of our ball bearing, you can sort of see how that ball rotates in a way that minimizes friction. While the outer race is rotating in one direction, the inner race is rotating another, the ball is simply rolling along such that it's in constant contact with both rings or both races. And by virtue of the fact that it is rolling, it means, or at least in principle, that that there is no sliding. And when we have no sliding, we minimize friction. Like I said, we can't eliminate friction. We can only ever minimize it. But the extent to which ball bearings can minimize friction is really quite astounding, which is why these little components can be found in so many machines today. So here's a cross section of all those components, at least the bottom part of the ball bearing. Now let's zoom in some more. Where the steel ball makes contact with the outer race, let's zoom in much greater resolution. Now the steel balls that are manufactured for ball bearings are usually very, very smooth. The races, the surfaces of the rings that touch the balls, yes, we try and manufacture them in a way that makes them really smooth, but it's a lot harder to machine out a beautifully smooth groove with certain geometries inside of a larger metal ring. Steel balls, they're much easier to manipulate. They're much easier to really control. They're much easier to polish. And so the steel balls are usually very, very smooth compared to the surfaces on the inner and outer races. So you can see we have in this cross section here, you can see that there is a machined but still imperfect surface on the outer race. Now, the steel ball's surface is machined but still imperfect. But its imperfections are vastly smaller than the imperfections associated with the surface of the outer race. And so that sets up the first phase of use. Now, the steel ball, you can see it rolling, or the direction of roll, I should say. Every time the steel ball rolls over this part of the outer race surface, I should say, essentially, it will experience a compression force. So the ball rolls over the top. It, as you can imagine, like a vehicle driving along the road, that's the road surface that experiences the vehicle driving over the top of it. When the vehicle goes over the top, we'll essentially feel that compression force from the weight of the vehicle. And the same thing happens with the steel ball. In this case, it's not necessarily the weight of the steel ball. It's more or less the weight or the forces that are required to hold the rotating shaft in place. So we have a very big compression force. And like I said, we are all about minimizing friction, but we never get rid of it entirely. So there will be a much smaller friction force that runs along the surface of this outer race. So that friction force exists. It's much smaller than compression forces, and by virtue of the fact that the ball is rolling, we can get that friction force down to a really, really small magnitude, but it's still going to be there. And so that's what we see every time the steel ball rolls across the outer race. And so the outer race, if we look at the actual outer race itself, which I've highlighted in this orange shaded region, it won't be perfect. It will also have, for example, defects. And that one defect that I've chosen to use in this illustration is hard inclusion. Now, high quality ball bearings are ball bearings that don't have a lot of defects, and the defects they do have are small. Again, you can never remove every single defect from something as large, at least from the atomic scale, as a ball bearing. And so there will always be defects. You can never eliminate defects. All you can do is control them. And we are getting really good at controlling those defects. And so this hard inclusion is perhaps something you would not expect in a high quality ball bearing, but it's something you would expect when you have some random Australian on the other side of the screen trying to illustrate a point. So we have this hard inclusion in this example ball bearing. The thing about hard inclusions, which is essentially an impurity, is that even though the inclusion might be perhaps really strong, maybe it's titanium, maybe it's something that's diamond, made out of diamond or something similar. Doesn't matter how strong it is, it represents a weakness because the hard inclusion involves a breakdown of the atomic lattice that we try to create when we create a steel alloy, which the outer race is made of. So even if the hard inclusion is really strong or comes from a material which is really strong, it represents a substantial weakness. And so when we're using our ball bearing, our steel ball will roll along the top of our surface, as you can see, and everything at this stage is cool. You can see the ball bearing rolling along very happily. The first thing that will happen in the life of a ball bearing, what we call phase one, plastic deformation. And that means, or that involves this very strong, smooth steel ball rolling across this rough-ish surface of the inner and outer race. And that steel ball will essentially smooth that surface. It will push down the peaks and push the peaks into the valleys, and you get a much smoother surface. And this is to be expected. This is what you expect to see from any ball bearing early on in its life. And so this is good. This is actually a good thing. You get smoother surfaces, which means that friction forces get smaller, and off we go. Now, once this has been happening for a little while, we will then move on to phase 2. And phase 2 involves crack initiation. And that's where we have these teeny tiny imperfections that are centered around, for example, surface imperfections and hard inclusions. And they will start to essentially grow into bigger defects, bigger weaknesses that will become the seeds of larger cracks. And we get cracks and cracking in lots of scenarios where we have cyclic stresses. So as you can see, the steel ball is still happily rolling across the surface. And every time it rolls across the surface, it exerts a big compressive force. And that compressive force disappears and the ball rolls away. And it exerts a friction force. It's much smaller, still there, and that friction force will also disappear when the ball rolls across the top. So every time the steel ball rolls across the top, another force is cycled through the structure of our race. And cyclic forces are the things that make cracks grow. So you can see we're starting to get these teeny tiny cracks initiate, micro cracks, will then become the initiating points of much bigger cracks, which leads us on to phase 3, a crack network. Now, a crack network involves these compressive forces taking those little imperfections which are starting to appear, and these compressive forces, compression forces, initiate a special failure mechanism. That failure mechanism is tensile fatigue. Now, tensile fatigue involves essentially forces pulling at the tip of the cracks, and the crack concentrates those forces so that you have these, you can see how these little micro cracks, you have these forces as they go through due to geometry, due to the fact that these micro cracks represent breakdowns in the structure of the material. You have these tensile forces essentially trying to pull the tip of the cracks apart. And so these cracks start to grow by experiencing tensile fatigue. So eventually, a large tensile fatigue crack will reach the surface. And so we will essentially get a dominant crack network around perhaps a hard inclusion or another surface imperfection. So if you want to extend the life of a ball bearing, try and minimize the number of imperfections. Try and have a beautifully smooth surface everywhere. Smoother the surface, the fewer the defects, the longer it's going to take for these cracks to start to emerge. And so phase 3, a crack network, it starts to appear where you have a bunch of cracks starting to hit the surface and then extend sort of a fair way down into the outer race material. Now, once we have the crack network, then we have phase 4, crack propagation. And this is where perhaps surprisingly the friction force takes over. So as the steel ball is rolling across the top, yes, it's still experiencing those compression forces. They have that much smaller friction force essentially pulling along the surface of the crack. Now that does a different thing to the cracks, especially the tips. This friction force now creates a shear fatigue failure mechanism. And as opposed to the crack tips being pulled apart, the crack tips are now being pulled along the line of the crack. So you can see here with the friction forces with that big crack which is emerging, the metal on the top of that crack is being pulled along the crack, and the metal on the bottom is being pushed in the other direction. So you have this tensile fatigue. And this behaves very differently, shear fatigue. And this behaves very differently to tensile fatigue. It just so happens that with this particular friction force and this shear fatigue failure mechanism, these cracks tend to grow at an angle of about 35 degrees beneath the surface of the outer race. in the direction of which the ball rolls. So they always start growing at a direction of 35 degrees beneath the surface until the cracks get deep enough that the friction force essentially starts to get, let's just say, muffled. Apologize if I'm getting a little bit too technical. The friction force will essentially then manifests itself on the crack tip, and that crack tip will then stop growing at an angle beneath the surface. It'll then start growing parallel to the surface. And then eventually, once you have this crack essentially creating a big loose bit of metal, eventually what will want to happen is this metal will sort of be vibrating up and down, and that crack will do a hard left turn and then head towards the surface. Now we have the crack going from one part of the surface beneath the surface and then re-emerging at another part, which leads us to phase 5, flaking. Flaking involves now a metal bit now disappearing. And we have this, the crack, which is now complete in terms of its journey down and journey back up, will then create a metal flake, which disappears, leaving what we call a spalled pit. And this creates detectable vibration. And so if you're in a manufacturing facility or something similar, you can put vibration sensors on ball bearings to detect when spalling is starting to occur. Now, when we have a single spall pit like this, the ball bearing is still working just fine. There's no problem with the how it's working. The problem comes when we move on to phase 6, that is expansion. And that essentially the spall pit then becomes the initiating site for more cracks, and always those cracks tend to grow again in the direction of which the ball is rolling. And so all these cracks are now relatively quickly propagating from the end of our spall pit, then more flaking occurs. Now, we have a problem. The ball bearing will eventually vibrate, create a lot of noise, heat, and decrease in lubrication. So what this means is essentially the real selling point of a ball bearing starts to disappear. We minimize friction by having a ball rolling across the surface. And when the surface is not smooth anymore, when it's going up and down, that's when those friction forces that were previously minimized start to ramp up. And those friction forces, which are now much bigger, obviously slow down or represent barriers to the torque. And importantly, they also represent lost energy. So as friction forces increase, essentially we're losing energy from our rotating shaft. That energy has to go somewhere. That is in the form of heat. And so if you have lots of spalling, you lose, your bearings start to not rotate as easily as they did in the past. And then eventually the frictional heat will increase to cause things to expand, which aren't designed to expand. As a result, the ball bearing might essentially explode. And I can see a chat from Shahid asking if this is the pre-Parameter Weibull webinar. And yes, it is. You're in the right spot. So let's have a look at this ball bearing from another perspective. And this is the view of the inner race. If we could hypothetically pull the inner race out of our ball bearing and observe it as it is degrading over time. So phases 1 and 2, where essentially you have the surface being smoothed out and cracks starting to grow. You won't see anything at the surface of the inner race. Phase 3, when you have a crack network emerging and starting to hit the surface, it will be visible if you're able to pull the inner race out of the ball bearing, and you'll typically see a V-shaped surface fatigue crack along the direction of ball travel because the friction force pushes the other way. And phase 4, where you have cracks growing beneath or cracks propagating beneath the surface, you won't see those cracks propagate. You'll just see this little chevron, this little V shape, until that crack hits the surface somewhere up above that chevron, and then you start to see flaking. So this is apart from that little chevron of a crack, the next thing you'll see is a spalled pit. And eventually, if you keep going, that pit will continue to spall, and a worn-out ball bearing race will start to look like this. So you can just imagine the amount of friction this is starting to create. Now, why am I torturing you with a deep dive of how ball bearings fail. There's two parts. There's two answers to that question. Two parts to the answer to that question. The reason being is because I'm trying to illustrate or explain a scenario where it's plausible for it to take some time before failure is possible. And so, from one perspective, if this is the random hand of failure, and this is for those people who are veterans of my webinars, you know what this represents. The random hand of failure represents all the different uncertainties and factors that influence how long it takes for something to fail. And how long it takes for something to fail is called time to failure. And time in this case is not based on calendar time or operational hours. It's based on cycles to failure. Now, cycles for a ball bearing. So in reliability engineering, we often use time to failure, or TTF, as a catch-all to describe essentially the age of your product. And if the age of your product should not be measured in terms of cycles, in terms of calendar time, then time is accepted, or time is understood to represent how you best measure the age of your system. So time to failure in this case could be measured in the number of cycles, the total number of cycles our ball bearing experienced before it failed. And so those 6 phases we went through: phase 1, plastic deformation; phase 2, crack initiation; phase 3, crack networking; phase 4, crack propagation; phase 5, flaking; and phase 6, expansion. Now, based on that explanation, from a physics of failure perspective, we would expect that if we know when phase 5 is essentially terminating, we know that failure cannot occur before phase 5 from our detailed understanding of how ball bearings fail. So this is a scenario where there might be justification for a failure-free period, at least based on how ball bearings fail. And that time we often denote with the symbol T subscript 0. Now, I need to be very, very clear about whether this is a thing for ball bearings, because this only happens, that explanation of how ball bearings fail is valid. It's true. That's how ball bearings do fail. And yes, hopefully you can understand philosophically, if nothing else, how there are certain steps that you need to go through before a ball bearing will eventually fail due to spalling. The ability for there to be a consistent failure-free period from one ball bearing to the next is relatively rare. And that only happens when you have very high quality ball bearings where the defects are all relatively consistent from one ball bearing to the next. And those ball bearings are being used in very consistent operating environments. When there's any deviations between build states and operating environments, the time it takes for each ball bearing to go through those first 5 phases is going to vary substantially. So the ability to have a single catch-all parameter describe a failure-free period for an entire type of set of components is relatively rare, but it can happen. The reason why we go through this perhaps painstaking analysis of how ball bearings fail is because you're not supposed to just do statistics. You're not just supposed to put numbers in and get numbers out and give the answer to whoever needs the answer for said question. Reliability engineering is all about understanding how your thing fails, and statistics is almost like the icing on that cake, where we sort of characterize our understanding. Now, T subscript 0, if this represents a failure-free period, for those of us who understand what Weibull analysis is, Weibull analysis involves fitting a probability distribution to a bunch of data we gather from test or field records to essentially help us try to characterize the random nature of failure. Now, most of the time, when I talk about Weibull analysis, the probability distribution we are looking at, as a rule, starts at 0, time equals 0. And after time equals 0, there is a finite chance of failure, and then there is a curve which sort of characterizes the extent to which failure is likely thereafter. Now, if we do that, we can now add this third parameter to our Weibull distribution, T subscript 0, to make it now what we call a 3-parameter Weibull distribution. So for example, here is the probability density function for a Weibull distribution. In this case, probability density function has a very bell-like shape. So it looks like a bell curve. It's not exactly a bell curve, but it looks like one. And this is because a Weibull distribution with a shape parameter of 3.5, you can see that 3.5 is on the right beneath beta. Beta represents a shape parameter, has a bell-like shape, very similar to a normal distribution. The second parameter, eta, which is a Greek letter eta, in this case is 12, and that's a characteristic life. So you can see for this Weibull distribution, probability density function has a bell-like shape, which is pretty symmetrically centered around 12. That's where those two parameters come into play. So a normal Weibull, not normal, let's just say a run-of-the-mill Weibull distribution, you can define its shape and its location with two parameters. Now, if you add t subscript 0 and t subscript 0 is positive, essentially all you're doing is pushing that probability density function to the right. You're adding a failure-free period. And if the failure-free period also happens to be 12, so if t0 is equal to 12, then essentially you're saying this bell curve only starts at time equals 12, and then the shape kicks in thereafter. So a three-parameter Weibull distribution allows you to move this probability density function essentially to the right. Now, question for you guys. What's the problem, or what's one potential problem with doing this for any item? It's a potential problem. Just degradation on the shelf. Yes and no, but that's would apply to anything. So Brian writes, there's no way to deal with failures less than T0. Corrosion, that's a failure mechanism. I don't think it touches on the question. It assumes no failure period. Like it. So Brian and Maximilian, you're on the right track. It's essentially telling, if you use a model, a three-parameter Weibull distribution with a positive T0, it's essentially saying there is absolutely zero probability of a failure occurring within period 0 to 12. In the real world, it's a big call. It's maybe certain scenarios where you could say that with some confidence, but to say that there is absolutely no chance that our ball bearing or anything else is going to fail in that period, it's a big call. Zubin says it doesn't account for random fails. All failure is random, so it still counts for the random nature of failure. Manufacturing defects may cause defects because I dare say you're suggesting that manufacturing defects may cause failures before T0. So you have a different failure mechanism. Love it. So there are a few caveats to adding a positive T0, or positive T0 to a three-parameter Weibull distribution. There's some, maybe if you understand how your ball bearing fails well enough, or your item fails well enough, you might be able to, with some confidence, justify a model which has a failure-free period. So that's just one thing that a three-parameter Weibull distribution can do. Another thing it can do is have a negative T0. Now, this sounds absolutely bizarre. How can we have a negative T0? You can see that for this bell curve, you have a negative T0, in which case it looks like negative T0 has a value of about minus 11, minus 10-ish. What that then does is essentially say, well, we're only going to look at the bell curve from, halfway into it, almost halfway into it. Now, this doesn't reflect a genuine failure process. It does reflect a bureaucratic process. What do I mean by that? Let's just say you work for a utility company, and for whatever reason, you lost all your failure data before T0. So you perhaps in September of last year, before September, you're recording data. In September, something bad happened. Maybe CrowdStrike was taking care of of the security of your IT systems. But unfortunately, as the very last thing that happened in August was you lost all your data, all gone. And so the data you now have is data you collected from the 1st of September onwards. So you know that the things you're looking at are older or were used before the 1st of September. But because you've lost all that data, you don't know when. And so you can sometimes use a 3-parameter Weibull distribution that gives you a negative T0 to help you characterize or estimate how long before your data was wiped, your thing was installed. And we'll just see an example of that quite short in the very near future. So a negative T0 can be useful for scenarios where you've lost data. You know your things were installed somewhere before T equals 0, 1st of September, the time you got your stuff back online. You say, okay, let's set that to time equals 0. You know things were installed or used before time equals 0. You just don't know how far or by how long. And so that negative T0, if you can do 3-parameter Weibull analysis, might help you work out how long ago that thing was installed. And another way you can have a negative T0 is if you have infant mortality or wear in. Why might we want to have a negative T0 if we have infant mortality or wear in? So before we talk about infant mortality or wear in, this blue probability density curve is what it looks like when your item is experiencing lots of infant mortality or wear in. That blue curve, which hugs the vertical axis, represents lots of failures occurring early due to manufacturing defects, or installation errors, or issues, or things like that. And so what you might want to do for components which you know are prone to have manufacturing defects or experience infant mortality, and we know when beta is less than 1, characterizes things with infant mortality. So you might want to expose those components to burn-in. And if your burn-in is going to last, also if you work at how long you want to conduct burn-in for, essentially you're taking the first little chunk of the life of your components and taking it away by conducting burn-in testing, where you put those components on some sort of test bed and you just essentially run them for a few weeks or months or however long it takes. The idea being is those with the biggest manufacturing defects are likely to be failing in that period, and those that haven't failed are unlikely to have big manufacturing defects, and so therefore they actually have effectively a much longer, much better reliability characteristics. But if you're trying to characterize statistically the effect of burn-in, you might want to use a 3-parameter Weibull distribution, because you know you have essentially this sort of initial period where you're essentially excluding failures. But hopefully you can see from this discussion is that I haven't looked at a single equation, haven't talked about anything else apart from scenarios where 3-parameter Weibull distributions might be helpful. And it's very, very important, because there are 4 well-accepted criteria that need to be satisfied before you can add or can consider adding a 3rd parameter to your Weibull analysis. And here they are. The first one is that you need to have a physical explanation for T0. So, for example, for ball bearings, you need to have a very deep understanding of how things fail, so you can explain with absolute conviction and confidence why it'll be physically impossible for a ball bearing to fail within a certain period. And again, in addition to the whole concept of those phases of failure, you need to make sure those phases are consistent from one ball bearing to the next. What that means is that you need to also be confident that the ball bearings are all high quality. Any defects they have are essentially consistent from one ball bearing to the next. They're all being used in a similar operating environment. So you really need to jump over a lot of hurdles to be able to convince yourself that you have a physical explanation for T0. The other explanations we looked at previously include, those scenarios where you lose all your data, so you don't know there is a T0, just don't know what it is, or you're conducting burn-in testing, so you are essentially taking off the first part of the operational life of certain things. There are other examples of you having a physical explanation for T0. The second criteria is that the 2-parameter Weibull plot needs to show a curve, and we'll talk about that very shortly when we come to probability plotting. I do another webinar. I've done quite a few webinars, I think, on Weibull probability plotting. I can't go into it in too much detail here, but long story short, a Weibull probability plot is able to arrange your data in a straight line if that data is resulting from a random process that can be described by a two-parameter Weibull distribution. So if there's a curve in that plot, it suggests that the two-parameter Weibull distribution is not necessarily a good model. So before you then use a three-parameter Weibull distribution, you first need to confirm there is a curve on that Weibull plot. We'll have a look at that in a minute. Third criterion is that you need to have a sample size greater than 20. When you have a sample size less than 20, it's not unusual to see the natural noise and variation in your test results show things that aren't there. So you want to make sure you have a good chunk of data before you start using a three-parameter Weibull distribution. And last but not least, you need to have a goodness of fit that exceeds other distributions. So if you're going to use three-parameter Weibull distribution, you have to first make sure you have that physical explanation. Second, make sure there's a curve in that two-parameter Weibull plot. Third, make sure you have a good chunk of data. And four, have a goodness of fit that exceeds other distributions. That includes the normal distribution, the log normal distribution, and other probability distributions that we can use to model failure mechanisms. So once you have these four criteria met, then and only then can you consider using a three-parameter Weibull distribution to help you out. So here is that probability plot or plotting paper what I was just talking about. So again, if you plot, you can see there's a really weird scale on the vertical axis for the CDF. And that's an artifact of this probability plotting paper. It's just by having this weird scale on the CDF, on the left-hand side, the percentage of things that are failing, and the horizontal axis is time to fail, and it too has not a weird scale, but it's a logarithmic scale. If you do test a system until it fails and get lots of failure data, and you plot those data points on this chart, and you see a relatively straight line, that's strong evidence to suggest that a two-parameter Weibull distribution might be a good model. If you have a positive T0, so if your thing is actually described by a three-parameter Weibull distribution which has positive T0, then your curve or your data tend to have a curve that looks like this. So this is potential evidence to support using a three-parameter Weibull distribution with a positive T0 value. If you have a negative T0 value, then your data will look like this. You need to be very careful because this curve here is where you sort of have a shallow start, sort of bottoms out, and then the curve increases, so the gradient increases at the end. This is also a symptom of the bathtub curve. So just seeing this sort of curve of itself doesn't essentially guarantee you have a negative T0. Just means, it could mean, I should say, that you have a complex system which wears in before it wears out. Now, let's look at let's look at a real example. So after hopefully now that you've seen what a curved data set looks like in a Weibull plot. So let's just say we are at that electricity generation plant and it has failure data on a number of ball bearings. And we know that these ball bearings are failing due to spalling. And these are big ball bearings. These are monstrous ones because we have big shafts doing lots of really important things. And so they're manufactured at very high quality. They're essentially tailor-made for our plant. So the first thing we might look at when we're trying to understand or ask ourselves, we're trying to understand or characterize the failure characteristics of this ball bearing, which we suspect is failing due to spalling, is just go through some rudimentary questions. Is there suspicion possible? Is it possible that our ball bearing could be failing due to spalling? The answer is yes. And if the answer is yes, does modeling the data with a three-parameter Weibull distribution help? Well, the answer is potentially yes. Could potentially be very, very, very helpful. So what you might want to do is if you go through those four criteria, number one, have a physical explanation. And if we convince ourselves that the ball bearing fails due to spalling and the ball bearings are very high quality, then yes, there is a potential reason for having a failure-free period. Remember, we need to see a curve in the 2-parameter Weibull plot. We'll have a look at that soon. We need to have a sample size greater than 20. In this scenario, we do. The goodness of fit needs to exceed other probability distributions. So let's look at what happens when they get some data from these ball bearings and plot it on Weibull plotting paper. This is what the data looks like. And you can see we have a line of best fit and a confidence region. So this is 90% confidence bounds. And you can see here that there is the back end of these data points genuinely looks like it's pretty straight. But the front end, you can see there appears to be a very significant curve. You can see there's a very sharp curve down. And so this is what you might expect. This is what you would expect if time to failure can be modeled by a 3-parameter distribution with a positive T0. And so obviously if you in my Weibull plotting course, I go through how you do this. This is from the Excel application that I have for said course. Now, essentially, you put the data in and you ask the computer, say, oh, what's the line of best fit and the confidence bounds associated with that line of best fit? You can see that's what the computer came up with. Now, then you can just essentially, in many cases, essentially tick a box and say, all right, can you do the same analysis, but instead of using a 2-parameter Weibull distribution, please use a 3-parameter Weibull distribution. And you can see this is the line of best fit and the confidence bounds for the best 3-parameter Weibull plot that our computer could come up with. Now, when it comes to 3-parameter Weibull distributions, there is no plotting paper where you can see a straight line. This is the best you can get because that T0 sort of messes up that logarithmic scale. So you can still see the line of best fit, you can still see the confidence bounds, but a 3-parameter Weibull distribution will not create a straight line on a Weibull plot, and that's because the Weibull plots can only focus on 2 parameters. So you can see here that we have evidence to suggest that a 3-parameter Weibull distribution might be plausible. So you can see the curve was as we would expect, and you can definitely see that the 3-parameter Weibull distribution does a much better job of taking into consideration that curve. Now, in another scenario, a utility company's maintenance data management system has failed. Failure data for a number of valves that are known to wear out was lost for a number of months. So no. And using the failure data that was generated when the system became available on the 1st of September, we need to try and work out when we think the original valves were installed. And so if we get our failure data for these valves that we started accumulating after the 1st of September, and we plot that failure data on a 2-parameter Weibull plot, you can see that there is ever so slightly a curve. You want to, when we have more than 20 data points, we have a physical explanation for T0, and you can see here that the data points at the top curve up above the line of best fit, as do the data points at the bottom. They also curve up. And so, all right, if we can conclude we can see a curve in these data points, so all right, computer, please give us your best shot at a 3-parameter Weibull distribution. Then in this case, when we ask a computer to do that, this is what we get. This is what the line of best fit looks like when you have a negative T0. In this case, the computer's best guess at T0 was negative 5.2. And so that might then tell us that our best guess at when these valves were installed was 5.2 months before 1st of September. So what's 5 months before September? So September's the 9th month, take 5 months, that's 4th. So 1st of April was 5 months before the 1st of September. So somewhere in March. This suggests that these valves were installed somewhere in March. And this just helps you, if that's an important number to understand to make decisions, then you now have a way of at least coming up with a relatively well-informed guess about when these valves were installed. Now, this might sound like a very manufactured example, but it's actually not, especially for utility companies which have, things buried in the ground for decades. When you bury things in the ground, pipelines and other things like that, you're not doing that with the anticipation of doing servicing. You also don't want to replace them every single year. They're supposed to last decades. And it's not unusual for decades-old data to be lost every now and then. And so you might have pipes and other infrastructure in the ground which were installed decades ago, but your data only kicks in over the last 15 years. When that happens, it can be really, really important to understand when you think those pipelines were installed in the ground, because that will then help you inform a decision about when you should consider inspecting / replacing those pipelines. And inspecting a buried pipeline is no easy thing. And so this can perhaps help you with that decision as we move along. So you need to be, hopefully you're sensing that you need to be very careful when using a 3-parameter Weibull distribution. But if you go through those 4 criteria, then there can be some really helpful information you might be able to get. Now, you might be asking us, in addition to some of the questions, the answers to the questions you gave me at the start of this webinar, why do we need to be very careful? One of the examples you gave was that whenever you have a failure-free period, that's a big call, really big call to suggest that there is absolutely zero chance something's going to fail for the first 20 years or months of the life of your system. So you need to be very careful for that reason and another reason as well. And we'll look at a scenario where we're trying to, let's just say we have a nail gun, and we have a nail gun that obviously is going to be pushing nails into wood. And when those nails get pushed into wood, we want those head of those nails to be flush with the wood. We don't want the nails to be launched into the wood at Mark 17 and essentially have the head a few millimeters into the wood. That's not ideal. You want the head to be flush with the wood, but you also don't want to have the pressure so low in the nail gun so that the nails don't go all the way in. So you want to get the pressure right, not too high so that nails go too far into the wood, and not so low so that the nails head stick above the surface of the wood. And I can see some questions coming through the chat window, and I'll come back to them in a minute. So let's just say we have some data. We're running an experiment where we measure how far above the wood the head of the nail is for certain air pressure settings for our nail gun. And that allows us to create this chart here. Horizontal axis, air pressure in terms of PSI. Vertical axis is the distance of nail head above the wood in millimeters. And of course, there's no universal air pressure because different nails, different lengths, different woods, they all influence how much force needs to be exerted to insert the nail the right distance. So let's just say we run one test at, in this case, 58 PSI, and it turns out the nail head for this nail was 0.73 millimeters above the surface of the wood. Okay, so experiment number 1, air pressure, 58 PSI. All right, the nail head is too high still. All right, let's do another experiment. This time, the pressure is a little bit lower, so we'd expect the nail head to be less, even further above the surface of the wood, and this is what we see here. You can see that second data point. Now, that allows us to draw a straight line. Now, this straight line has 2 parameters. So this is the equation for that straight line. D equals minus 3.710 times P plus 3.185. D is the distance of the nail head above the wood, and P is the air pressure in PSI. And so you see we have 2 numbers left in this equation. They are parameters. These are numbers we can essentially control or fine-tune to make sure this line passes through our data points. And so we have 2 data points and 2 parameters. And so we now have a perfect model because parameter number 1, negative 3.710, and parameter number 2 are just right so that it creates a line which goes straight through the middle of these 2 data points to create a perfect fit. This is fantastic. It's what we want. Now let's just say we did another experiment. And before we move to another experiment, this straight line tells us perhaps that our best guess at the optimal air pressure is perhaps around about 97 PSI. But of course, we want to have more than 2 data points. So if we do another test, and this time we test at about 15 PSI, and you can see the nail head is even further out, you can see that this data point on the top left-hand side is no longer a perfect fit. Well, one way we can overcome that is by increasing the complexity of our model. And we can add another parameter using another term, p squared, this becomes a polynomial model where we essentially have it's expressed in terms of p squared, p cubed, and so on and so forth. By doing this, we now allow us to have a third parameter, and we ask our computer to find the model using this now three parameter model that is now a perfect fit. It comes up with these numbers, and the line now passes again through all the observed data points. So we have a perfect fit again. And so this now even better perfect model now lines up, suggests that the optimal pressure should be 85 psi. You can see we have this way more sophisticated model, much better estimate of the optimal pressure for our nail gun. But of course, let's do some more testing. And here, oh, geez, here we have a data point all the way over there. That's really ruining our chi. Now our data is no longer perfect. So what can we do? Well, we can add another parameter to create this model here. Now we have a perfect fit again. But you can see stuff is getting crazy. We now have a wavy line going through our data points with this perfect fit. You can see that it's suggesting that if we increase pressure up to 100 psi, then of course the head of the nail will get further or get closer and closer to the wood surface. But once we keep increasing pressure thereafter, for some reason this model is telling us that the nail head will be further away again. That doesn't make a lot of sense. I say we'll do some more testing, see if we can improve our model. Here's another data point. Now we have a 5 parameter model. And look what this is suggesting over here. It suggests that, hello, if we have 0 psi, like no pressure in our nail gun, then our nail will go all the way in and our nail head would be flush. All right, let's try and improve our model, do some more testing and now add another data point and now come up with an even better model, which has 6 parameters. Again, our model is perfect, but you can see that essentially this is getting very, very silly. You need to be very careful when it comes to adding parameters, because adding parameters will make your model fit better every single time. But let's go back to the real world. If we look at these 6 data points, hopefully you'll agree with me, they do appear to create a straight line, at least in this chart. And so using these 6 data points, we have an imperfect model in that there are differences between what the model suggests and what we observe. But you can see with our human intuition, these blue data points appear to be creating a straight line. And the fact that these blue data points deviate away from our best guess at the model is understandable, because inserting a nail into wood is a random process, or how far a nail goes into wood is a random process. You might hit a bit of wood where there's a knot, or the nail gun might not be perfectly perpendicular to the wood when the air pressure is released, etc., etc., etc. So there's always going to be some noise. So if you overfit a model to your data, you get those crazy models we just looked at previously. So it's always important to take a step back and see if there's a genuine trend and a simple model that explains what's going on. Because if you do agree with me that it appears to be a straight line going on, then our best guess at the pressure setting is 128 psi, and we can add confidence intervals around our line of best guess to help us understand the uncertainties in that best guess. But that whole idea of trying to find the perfect model, that's called overfitting. A lot of statisticians do that. And why is that important for the 3 parameter Weibull distribution? And that's because that every time you add a parameter to a model, including going from a 2 parameter distribution to a 3 parameter distribution, you will get a curve that fits better. Problem with that is, while the curve fits better, it might introduce nonsensical characteristics. In this case, we had nonsensical characteristics where one model suggested the air pressure needed to be 0 psi. Another model suggested the air pressure, once it went above 100 psi, would essentially result in the nail head being further and further away from the wood. So you only ever add parameters if you know why you're doing it. So I'm going to open it up for questions. When I say opening up for questions, first thing I'll do is go through the questions I see compiling up in the chat window. So Carl writes, service life prediction and modeling, service life expectations definition, performance criteria using science performance requirements, sustainability and service life, Any thoughts? Carl, I'm going to be honest. That's a huge raft of concepts. So I'm going to need you to be way more specific because, of course, I've got tons of thoughts about all those things. However, and you talk about three components of service life, include technical, function, economic. Any thoughts? Again, tons of thoughts, but it's such a wide-ranging grab bag of ideas that I'd probably need you to be way more specific if I was going to have a detailed answer to it. And you talk about, Carl, three measures of performance include sustainability or life cycle assessment, resiliency or resistance to degradation, and life cycle cost analysis. Any thoughts? Again, that's such a huge, wide-ranging set of subjects in that question. I'd have to ask you to really focus on a particular question. Julia writes, is this only apply or only applicable to devices that all started their service life at approximately the same time? Julia, I believe you're referring to the negative T0 scenarios where, for example, we lost data before a particular point in time. We're trying to estimate how long ago that thing was installed. You're 100% right. That's for a set of things which we believe were installed at the same time. If those things that create those data points weren't installed at the same time, effectively it means that each different device has a different T0 value, and it's going to be impossible to work out when you combine all those data points together what the T0 value for each item is. So it's a really good question. And yes, it only does apply to devices where we have reason to believe they're all installed at the same time. Kenneth writes, could absolutely be failure via corrosion or other sitting on a shelf in a humid warehouse. Not really failure-free time. Not entirely sure. I might have missed the context for that question. My apologies. And we ask the classic bias variance trade-off. Happy with that. Essentially, you're talking about where you have a better model or a more perfect model. It reduces the variance, the dispersion between your model and data points, which is great, unless that model introduces nonsensical behavior. The Weibull distribution is used to evaluate the reliability and material strengths of various items. I wouldn't agree necessarily with material strengths, necessarily, such as vacuum tubes, capacitors, ball bearings, and relays. Time to failure, yes. The distribution is flexible and can model hazard functions that are decreasing, increasing, or constant. Yes. The importance of the Weibull distribution lies in its flexibility and ability to capture a wide range of failure patterns. Yes. Adjusting the shape and scale parameters can model various failure behaviors such as early failures, constant failures, or wear-out failures. Yes. Any thoughts? Well, those are statements I'll all agree with, Carl. Let me say that. Let me just say that, I should say. The Weibull distribution is fantastic. Helps you characterize all sorts of different failure mechanisms. It's from the family of extreme value distributions, and because it's from the family of extreme value distributions, it sort of mimics or models things which fail when the last thing fails out of a bunch of things, or the first thing fails out of a bunch of things. So it's great for scenarios where things fail when the weakest link fails, or things fail when the strongest link fails, which often happens at the microscopic level in failure mechanisms. So the Weibull distribution is such a universally useful distribution because it can model lots of different scenarios. Any other questions or comments? What about using non-parametric approaches instead? So, for example, the Kaplan-Meier model, what's not model, but the Kaplan-Meier approach. Yeah, non-parametric models can be very, very useful because they don't rely on you assuming an underlying model. The problem with non-parametric models is you need a ton of data to get anything useful. So if you have reason to suspect that the Weibull distribution is a good fit, we know, for example, we know that when tires wear out because they uniformly lose tread as they get driven over roads, and so the bell curve does a really good job of modeling time to failure for tires. Whenever you have the ability to use a model based on your physical understanding of how things fail, assuming a model represents a ton of information. And so when you have a ton of information through a well researched model, you need to test less. Non-parametric approaches, where you don't assume a model, you don't get all the information from understanding that tires wear out in a pattern that's described by a bell curve. You need to replace that information with lots of data. So non-parametric approaches can be very, very powerful. It's just that you need tons of data. A scenario where you see non-parametric models is those SN curves for fatigue. Essentially, for every alloy that's been smelted, there are laboratories across the world which take samples of that alloy, and then they test those samples in laboratory conditions for fatigue. And you essentially have thousands upon thousands of samples being tested to create the SN curve. So non-parametric models are very powerful for that sort of stuff. But yeah, you need a lot of data. Okay, if my fatigue data best fit to a 3-parameter Weibull and it suggests a failure-free period, can I apply 3P? I don't know for absolute certain if there is 0 chance of failure before that T0, but I can think of some reasons. I'm going to put this back on you. The 4 criteria I talked about need to be satisfied. So, like I said, every time you add an additional parameter to a model, like every time you go from a 2-parameter Weibull distribution to a 3-parameter Weibull distribution, you allow essentially the computer more flexibility to find an even better line of best fit. So I'm not surprised. Well, it's a 3-parameter Weibull distribution fitting your fatigue data better than a 2-parameter Weibull distribution is exactly what I would expect. But that does not mean that the actual data comes from a process as described by a 3-parameter Weibull distribution. So I went through 4 criteria. So I'm going to put it back on you. Are those 4 criteria met? If the answer is no, then 3-parameter Weibull distribution is not for you. Carl talks about how non-parametric methods tend to be more accurate as they seek to best fit the data points. I would push back on that. If you have reason to suspect or conclude that, for example, a bell curve models time to failure for a tire, then the results you get from 5 data test involving 5 data points is going to be way more accurate than any non-parametric model. And then these methods tend to be less efficient when it comes to training the models. Yeah, again, I think that's a very statistical perspective. If you understand the physics of failure, and we know, for example, fatigue tends to be well modeled by a log normal distribution. Tire wear out is modeled by a bell curve. We know this because we understand how those things fail. So that's where it's always important to understand how your thing fails. And if you can usually come up with a model or usually know why a model should apply to your failure scenario. And that, if you know that represents a ton of information that could replace thousands of data points you otherwise have to test. Thank you, Anantha Krishnan. So I'm sorry if I mispronounced your name. Anantha Krishnan. Is that anywhere close to? Hopefully I didn't get it too wrong. Okay, Kwang has come back. It fits all other criteria. Curve in 2P, more than 20 data points, best fit with 3P. The one thing you haven't talked about is your fatigue. Is there a physical reason why you would have a failure-free period? Not just a speculative reason, not just a theory. Is there an actual reason that you know would apply to your scenario, which would result in a failure-free period? Suspicion of existence of different failure modes in Weibull or T0. Any thoughts? Yes. If you have different failure modes or mechanisms, then of course this tends to break down a little bit. So I've done other webinars which we talk about where I go through what you can do with a Weibull plot which has different failure modes. But as soon as you have different failure modes which imply different failure mechanisms, so one component's failing due to corrosion, another one's failing due to misaligned bearings or what have you, then essentially the modeling breaks down. 4 criteria of good data model. Data in a good model can be easily consumed. Large data changes in a good model are scalable. Good model provides predictable performance. A good model can adapt to changes in requirements, but not at the expense of 1 through to 3. Those criteria apply to models more broadly. when it comes to, and that usually is where you're trying to get those, for example, modeling a physical characteristic that you're trying to predict in the future. When it comes to reliability, it's all about the model can be as good as it can be, but look at those confidence bounds. Those confidence bounds are a way of characterizing the extent to which those models don't do a good job of fitting. And so, yeah, there's lots of things you can unpack in those for, but they're more applicable to some more physics-based modeling. Oh, thanks, Greg. Much appreciated. Thank you, Carl. My name's Chris. That's right. Carl's the one who's firing lots of questions my way. Thank you, Michael. Choose the right model. You need to define the problem, consider the data, evaluate different models, consider model complexity. Yes, you need to do those things. But the one thing I would suggest is try and look for the simplest explanation first. Whenever you have, like I said, additional parameters will always make the fit appear better, but it might introduce crazy scenarios or crazy phenomenon that are not going to be seen in the real world. Thank you, Nazri. Again, apologies if I'm mispronouncing names. I've been teaching a course to Australians to all hours of the night last night, so my ability to speak the English is quickly wearing away. I've got a different sort of fatigue failure mechanism going on at this end of my microphone, so hopefully I was intelligible enough to help you guys out. Thank you, Gouling. Thank you, Kingsley. Yes, I am in wear out. So it sort of kicked in once I got married and had kids as well, so I think there's a couple of failure mechanisms going on. No worries, mate. Thanks, Antonio. I think we're sort of exhausting the well of questions, Fred.
Yeah, I think so. Another good one. And as usual, I have no idea what your next one is, but I'm sure it will be entertaining and informative. So stay tuned.
Let me try and remind myself what it is. It is coming up slowly. It's all about fault trees, Fred.
All right, that'll be good. And
Ultras and
one
RCA.
thought when you were going into the ball bearings in depth like that, and we might have to think about a whole series just on failure mechanisms.
Maybe.
What is like solder joint cracking?
Yeah, that's such a good idea.
It's a different phenomena than ball bearings falling, and there's plenty of failure mechanism out there. We'll have another couple months worth of webinars then.
Yeah, because I mean, like if you know how things fail, I mean, knowing how a ball bearing fails means that you're aware, you're more informed about how to maintain them, how to select them, how to install them in a way which extends their life. And so that's the power of understanding how things fail. You can correctly select them, correctly design them, correctly install them, correctly maintain them. If you know how they fail, you know that a vibration sensor can give you warning of impending failure, all because you know how ball bearings fail. And I think with solder, Fred, noting the issues emerging with low temperature solder, that would be perhaps a really useful webinar.
Yeah. Now we'll have to add that to the bailiwick here in the future as we suss out what else to talk about.